everyone, welcome to the course of Real-Time Embedded System. Today we are going to start chapter number 5 and we will continue chapter number 5 of the Wine-Wolf book, and we are studying program design and analysis in this chapter. So let's get started. So in previous couple of lectures we talked about compilation flow, we talked about basic compilation techniques, and today's lecture we will focus on basic program optimization. So let's see what are those basic program optimizations. So the basic program optimization comprises of expression simplification, deadlock elimination, procedure inlining, loop transformation, register allocation, instruction scheduling, and instruction selection. We are going to look at each one of them one by one with few examples. So let's start with the expression simplification. Expression simplification is a useful area of machine-independent transformation. So the first thing that you can do in expression simplification is that constant folding. Rather than using 8 plus 1, which is 8 is constant, 1 is constant, we can directly use 9. So using variable instead of constant can simplify the expression. Number second is algebraic. We can use laws of algebra to simplify expression. Consider the following expression: a multiplied b plus a multiplied c is equal to a multiplied b plus c, which is like distributive property. So in one case you can see that we have three operations, that is a multiply b plus a multiply c, whereas in later expression we have just two operations, a multiply b plus c. Since the new expression has only two operations rather than three of the original form, it is almost certainly cheaper because it is both faster and smaller. Such transformation makes some broad assumptions about the relative cost of operation. In some cases, simple generalization about the cost of operation may be misleading. For example, CPU with multiply and accumulate instruction may be able to do a multiply and addition as cheaply as it do addition. However, such situation can often be taken care of in code generation. So we can also use the laws of arithmetic. As I've told you, we can use the laws of arithmetic for the purpose of constant folding to simplify the expressions. And lastly, we have strength reduction. In strength reduction, we use basic operation. Like for example, we are doing a multiply by 2. So if we are able to do the similar thing with the help of addition or subtraction, because the strength of multiplication is more compared to subtraction and addition. Similarly, a multiplied by 2 is equal to a less than 1. So we can use simpler operation rather than these multiplication and less than to reduce the strength of the expression and to fast the code execution. So let's move on to next slide. So in this slide we are going to talk about dead code elimination. Code that will never be executed can be safely removed from program. The general problem of identifying code that will never be executed is difficult, but there are some important special cases where it can be done. Programmer will intentionally introduce dead code in certain situations. For example, you have a code in front of you. Hash define debug 0, it means debug has a value of 0. If debug, it means that this if statement is going to be false every time. So this portion will not be executed. What we can do, can eliminate by analysis of control flow. So this is a control flow. You can see this is the control flow. So okay, so this thing is wrong. It should be here. Okay, so the condition is always going to be wrong. So we are never going to come and execute this. So we'll always exclude this and exclude this. Okay, so we can exclude both of these. In this case, dbgp1 function is never executed but the code allows the programmer to override the preprocessor variable definition to enable debugging code. This case is easy to analyze because the condition is the constant 0. So this condition is constant 0, which C uses for false condition. Since there is no else clause in the if statement, the compiler can totally eliminate the if statement, rewriting the controlled data flow graph to provide direct edge between the statement before and after. So direct edge between the statement before and after. Some dead code may be introduced by the compiler. For example, certain optimization introduce copy statements that copy one variable to another. If uses of the first variable can be replaced by references to the second one, then the copy statement becomes dead code that can be eliminated. Let's move on to next slide. So another machine independent transformation that requires a little more evolution is procedure inlining. So procedure inlining eliminates procedure linking overhead. So this is how we can optimize our program. So you can see that we have function definition, this is function definition, then followed by this we have function call, and then we have a inlining result. So an inline procedure does not have a separate procedure body, so we do not have a separate procedure body here, rather we have the body in the same file followed by the function definition. Rather, the body of the procedure is situated in place of procedure call. The C++ programming language provides an inline construct that tells the compiler to generate inline code for function. In this case, an inline procedure is generated in expanded form whenever possible. However, inlining is not always the best thing to do. So, for example, we are going to use this function and function call 10 times in a code. So it will make the code lengthy and we will repeat the same thing and again and again. However, in a cache system, having multiple copies of the same function body may actually slow down the fetches of these instructions. So if we have like 15 times this thing written in the same code, so it will slow down the fetches of the instruction. Inline also increases the code size, and ultimately it will increase the memory, which is very precious. So this is the advantage of procedure inlining, that it eliminates the linkage overhead. However, it can also increase the size of the code and size in the memory and also slow down the fetches. So let's move on to next slide. So another optimization is loop transformations. In loop transformation, our goal is to reduce loop overhead, increase opportunities for pipelining, improve memory system performance. Loops are important program structures. Although they are compactly described in source code, they often use large fraction of computation time. Many techniques have been designed to optimize loops. So let's talk about these techniques. So loop unrolling is a simple but useful transformation that reduces loop overhead, can reduce test instruction and branch penalties, expose potential parallelism. So here you can see we have this original code with 4 times unrolling. So it means that it's going to run from 0, 1, 2 and 3. So what we are doing, we are multiplying these two statements for I is equal to 0, I is equal to 1, I is equal to 2 and I is equal to 3. So we are unrolling the loop 4 times. Whereas here we have reduced the loop overhead and we are just unrolling the loop for 2 iterations, 0 and 1. However, we have done parallelism here. Here you can see that we have 2 statements. B and C are multiplying, B and C are also multiplying here. So in this case, since all operations in the 2 lines of the loop body are independent, later stage of compiler may be able to generate code that allows them to execute efficiently in CPU pipeline. So these two statements are independent. So what we have done, we have introduced parallelism here. So in the next stages, the compiler may be able to generate code that allows them to execute efficiently on the CPU's pipeline. So here we reduce the loop unrolling. So here it was unrolling 4 times, here it is just unrolling 2 times and giving us the same result. So let's move on to next. So loop fusion basically combines 2 or more loops into a single loop. For this transformation to be legal, 2 conditions must be satisfied. First, the loop must be iterated over the same values. Second, the loop bodies must not have dependencies that would be violated if they are executed together. For example, if the second loop's ith iteration depends on the result of the I plus 1th iteration of the first loop, the two loops cannot be combined. The loop distribution is the opposite of loop fusion. So here you can see that we are going to combine two loops into a one loop. Same number of iteration, no dependency between the loop. So here you can see that we have one loop in which we are multiplying b with 5 and so storing its array elements in A, and n can be any number, and here we are also multiplying C and D and we are storing the result in W. So we can see that there are no dependencies between these two loops. What we can do, we can start a loop from I is equal to 0 and go to the same length. Okay, so same value over which the loop is going to iterate. Now what we have done, we have combined these two because these two statements were independent. They do not have dependencies. So we have used the same statement, A of I is equal to B of I into 5, and then we are going to use W of I is equal to C of I into D of I. So fusion means combining the loops, and its opposite is loop distribution. Mean from one loop we can go to two loops. Here we are going from two loops into one loop. So by doing so, we can optimize our program. So this is another type of loop transformation. Let's move on to next. So the final loop transformation is loop tiling. Loop tiling breaks up a loop into a set of nested loops. So here we are going to break the loop into set of nested loops. Changes order of access within the array. Changes cache behavior. So this loop tiling will change the behavior of the cache by changing order of the access within the array. The way we are going to access the array elements will change the behavior. So let's look at, so as we have talked previously that we can break up a loop into nested loop. So this is loop tiling. As you can see here we have only one tile, here we have two tiles, 1 and 2 tiles. So what we are going to do, we are going to break this loop into two. So for I is equal to 0, for I is equal to, for I is equal to I, and for j is equal to 0, we are going to break this into j is equal to 0, and for jj is equal to 0. So here we have just one tile. This solid line represents I. For every I, we are going to run jn times. Okay, so these two. So here we are just moving along the rows. Okay, so this is slow as compared to this one, the right one, where we are moving in rows and columns. So this is our row and this is our column. So here we have two tiles. Okay, tiles of size 2. Each loop is split into two loops. For example, the inner II loops operate within the tiles. So the inner II loops operate within the tiles. So this is our II. And the outer I loops iterate across the tiles. So this one, the second tile, is basically our I loop. The result is that the pattern access across an array is drastically different. Rather than walking across one row, the code walks through rows and columns following the tile structure. So this is what happens when we do loop tiling. We move from row to column. Okay, rather than walking in a row, we walk through rows and columns. Loop tiling changes the order in which array elements are accessed. So you can see that we have loop for ii is equal to ii is less than minimum of I plus 2 comma n and ii plus plus. So what happens? It changes the order in which array elements are accessed, thereby allowing us to better control the behavior of the cache during the loop execution. So this is the last optimization or loop transformation. In tiling, we basically break a loop into nested loops. Why? So that we can change the direction, change the access of the cache. So in previous slide we have seen that we can use loop tiling to change the behavior of array, how it is accessed in cache. We can modify the array being indexed in loop by array pairing. Array pairing adds dummy data elements to a loop in order to change the layout of the array in the cache. Although these array locations will not be used, we are not going to use these array locations. So previously we had 0, 0, 0, 1, 0, 2, and now we are going to change the layout. So we have added an extra element at the end of first row and extra element at the end of second row. So although these array locations will not be used, they do change how the useful array elements fall into the cache lines. So that was about array pairing. So we just add some data at the end of the rows. And why do we do that? We do that in order to reduce the conflicts. So there will be minimum chance of conflicting of first row with the second row. So another way of program optimization is register allocation. We can optimize our program by efficient use of register, determine lifespan of a variable in the register, to reallocate the register to new variable. Reordering operation can change required register, and you can see the example that is mentioned in your book, and basic case within the basic block. So register allocation is very important compilation phase. Given a block of code, we want to choose assignments of variables, both declared and temporary, to register to minimize the total number of required register. So our goal or our aim is to optimize the code by reducing the number of registers used. So we can explain this with the help of examples shown in next. So in this particular example, register lifetime is shown in the graph, and these are the three statements in which we have 7 variables, and there is a restriction in this example that we are only allowed to use 4 registers of the ARM. However, if we think that each variable requires one separate register, we will be needing 7 registers. However, we can reuse the register once we are done using the stored value in it. We can do much better by using a register once the value stored in the register is no longer required. For example, in the first statement a plus b, the results come in W register, for example. Now we need to use W because W is being used in next statement. However, x is equal to c plus W would not require the value of x because x is not being going to use in next statement. So we can reuse this register. To understand this, we can draw the lifetime graph that shows the statement on each statement is used. So here we can see which variable is used in each statement. So if you see that the time basically defines statement, so A and B, and the result comes in W. So in that particular we are using three registers, and then we hold the value of W because in the second statement we are going to add C with W and the result will be X, and then we will hold the value of C because we are going to use this register again. So C and D. what we'll get? Y. So a horizontal line stretches from first statement where the variable is used. So we are using this variable, that is C, in second statement to the last use of the variable. So here's the last use of the variable, this statement 3. A variable is said to be live, so the variable is live in this state. The variable is live here, okay? During the interval, at each statement we can determine every variable currently in use. So at every statement we can see that these three are used here, these three are used. The maximum number of variables in use at any statement determines the maximum number of registers required. In this case, statement 2 requires 3 registers. So here we can see that statement 3 requires, basically statement 2 requires 3 registers, C, W and X. This fits within our 4 register limitation. So we are using only 3 registers whereas we are allowed to use 4 registers. By reusing register once their current values are no longer needed, we can write code that requires no more than 3 registers. So there is an example in your book regarding to this, in which we are just going to use 4 register. So once, for example, you needed more than 4 register, we can use those registers that are not in use. So that is about register allocation, how you are going to allocate register to the variables. So let's move on to next slide. So the second last technique for program optimization is instruction scheduling. Non-pipeline machines do not need instruction scheduling because we cannot execute 2 instructions at a time. Any order of instruction that satisfies data dependencies run equally fast. In pipeline machine, execution time of one instruction depends on the nearby instructions. So as we have seen from our previous program that we can use data flow graph to represent the model of the code. So here you can see that we have 5 statements: w is equal to a plus b, x is equal to a minus c, y is equal to x plus d, x2 is equal to a plus c, and z is equal to y plus e. Here we have a single assignment, so it means that each statement is uniquely identified, and that's the, in front of it you can see the data flow graph where we have a, b, c, d, e. All these are what? These are nodes, and these are input nodes, and then we have operational node that is plus, plus, minus, plus, plus. So these are our operation nodes and these are our data input nodes. So this a plus b is basically a basic block. Okay, so in previous lecture we also discussed that the arrangement of the order of the operation also make a significant effect on the pipelining. So we can reorder our operations so that, for example, if a plus b gives us the result of w and w is required in the next statement and it is not available, for example, then we have to wait. So we need to arrange our code or basic operations by seeing at the data flow graphs that no stalls happen. So we can reorder operation to reduce pipelining conflict. If there is any pipelining conflict, we can reduce those pipelining conflicts. And by doing so, we do not need to access memory again and again. So we can hide the memory latency. So in this slide, we are going to talk about the last method of program optimization, that is instruction selection. So selecting the instruction to use to implement each operation is not trivial. It means that we can have several methods or several different instructions that can be used to accomplish the same goal, but they may have different execution times. Moreover, using one instruction for one program, another instruction for other program or the same program can result in a conflict or the problem arises. So what we do, we basically use templates. So we use built-in templates or template matching to use the same function to implement the task. Represent operation as graph. So we represent operation as graph. As you can see in this, we have expression, plus and multiply. So for multiply and plus, what we are going to use, we are going to use mul, add, or if we have m add, it means multiply or added, we are going to use this. So represent operation as graphs, match possible instruction sequence onto the graph. So what we are going to do, we are going to check at the instruction, then we are going to map that instruction on the graph using the template matching. So using your own compiler, there are different levels of optimization available for the compiler, that is test 01, 02 and so on. Look at mixed compiler assembler output. We know that compiler can vastly transform your program during the creation of assembly language. Compilers are also substantially different in terms of optimization they perform. Understanding your compiler can help you get the best score out of it. So we can look at the mixed compiler assembler output. We can modify compiler output, which requires correctness and it requires loss of hand tweak code. So if you write your own assembly code, you must ensure that it conforms to all convention, such as procedure linkage. If you modify the compiler output, you should be sure that you have an algorithm right before you start writing code, so that you don't have to edit it repeatedly. That's it for today. Thank you very much.